Good morning, everyone. Welcome. My name is Maria Zamora. I'm a newish assistant professor at OSU Extension, working statewide on irrigation and agricultural water management. Happy to be here, and hopefully you can learn new terms or new strategies during our conditions, but overall is a refresher of things that you should be doing or things that you could be doing. And this could be a foundation for future workshops in which we can cover multiple other things, because irrigation and water use is pretty broad. Thank you.
Hi, my name is Garrett Gibson, and I'm an engineer with Natural Resource Conservation Service. I am going to talk to you today about using an application from WSU. It's an irrigation scheduler that uses live weather data, and I'll get into the details in a bit.
Hi everyone, my name is Abigail Tomasek. I am also a newish assistant professor in the Crop and Soil Science Department at Oregon State University. I'm based out of Corvallis, but I have statewide responsibilities. So my official title is the Extension Soil Water Quality Specialist. So I'll be talking about a little bit about how you should consider water quality and soil quality when you think about irrigation.
I'm Todd Peplin. I am with the Deschutes Soil Water Conservation District. I am retired Natural Resource Conservation Service back for 30 some odd years. I used to be the district conservationist here in Central Oregon back in the 90s. Soil scientist prior to that. In '87 published the Warm Spring Soil Survey and worked a little bit on the upper Deschutes. Well, welcome. Thank you all for showing up. I really appreciate this. This is going to be a real brief overview, and you get to have a test here. A couple things we're going to go over is your basic about soil particle size, pore space, permeability, infiltration, how water relates to soils. But I always like this. The other day I was looking at this slide and I was like, this is actually a really cool slide. The reason being because this is what you're going to be talking about. Maria's going to be talking about this, Abigail and Garrett, because this is the soil profile. This is what you're going to be looking at, is how water actually, infiltrates into the soil, how that stays in this soil profile, how you're going to manage within this section right here. It puts it into perspective. I think a lot of us, we get complacent, we irrigate, we just don't, either we got other jobs, we go to other jobs, and then we come back and maybe change the irrigation system or whatever. Hopefully we can break you a little bit about that, but there is management that you have to do. But to start this thing off, the soil is the medium. The soil is, we need to know what the interaction of water going into the soil profile is. We need to know how the water and the crop utilizes the uptake of that water to get your optimal growth and to get your best, either your hay production or your grape production or your lavender production or whatever you're growing. You really need to manage this so nothing goes this way or evaporates. So next slide. I always look at this slide here and there's a lot of things that deal with soil texture, okay? Just remember, soil texture are particle sizes of sand, silt, and clay. Everybody, looks at this thing. Does everybody know how to work this thing? Everybody sees it and they goes, I think I do. Okay, so basically how this textural triangle works is basically if you got sand particles, it usually is a field. I have a class that's really fun. You get over here, you get dirty, you get the feel stuff, and you kind of guess how much percentage of sand, silt, and clay it is. But this is a chart that you could go, oh, well, if I feel this much 60% sand or this much clay, let's say it's 10% clay, and silt is maybe around 40%, it's going to land me right here in the sandy loam. And that's what that textural triangle means. But what we're going to be looking at is size. The bigger the size, the bigger this pore space. So over here in this little beaker, and I'm going to do really quick because I don't know if we're going to have enough time to do that. I want to make sure about it. But we figured this out. Your sand particles are basketballs, baseballs, or whatever balls you want here, or marbles. okay, they are your biggest size of particles, which, yeah, if you put water on it, right, it just whips right through there, okay? Why is that, okay? Well, it's because when you put these baseballs or basketballs together, there's these things called pore spaces in it, and that's what makes it go through faster, okay, infiltration. When you have a silt-sized particle, it gets a little bit more smaller, and that's what that is all about. Now, it kind of comes through. Why is that? Because there is a lot of surface area that goes along with that, so there's lots of little pores. But in this case, usually silt will not particularly go this far. This will go faster than this, believe it or not, but it's holding up here. The reason why is you get a lot more pores, water is infiltrating in, it has a lot more surface area to get into it, but it will hold that water a little bit more, but it'll infiltrate in a little bit less, as opposed to the smaller particles, and I do believe that's clay. I hope that's clay. Well, clay wouldn't do that, but but it's close. So really, when it comes down to your clay particles, that would have just sat there if that was 100% clay. It would just sit there for a long, long time. Silt, that is not really silt, and what that would have done would have come in a little bit more slower. And again, it deals with pore spaces, okay, within the particle size. So as they come together, and I like doing this little idea here. Okay, so basically in between this space here, these are pore spaces. Okay, the bigger the size particle, the bigger the hole, let's say, okay, basic principle. When you're irrigating and you see the water being applied to the ground and it's going in, we call that infiltration, okay? Okay, so.
One thing I'd like to point out is if you do look at the soil, so you can see like in the silt, there's a little bit of water still held below here. In the sand, there's none. In the clay, all of this is still saturated. So depending on your pore space also affects how well the soil can hold the water.
Perfect, and that is a good point. You got into my next slide, which this is kind of neat. So again, kind of reiterating what we're talking about, infiltration, but this is exactly what Abigail's talking about here, is with clay, it takes a heck of a lot of water to fill up that clay in that clay profile, if you will. But the thing about it is not going to be, you need a lot more water to have it available to your plant, and we'll get into that in a minute, as opposed to a sandy loam, where you have your sands will just come in, bigger pore spaces, water goes through. You need to have, this doesn't have a lot of holding capacity, so your available water for that plant isn't going to be much. So I always do this lovely little trick here, and now this is your test time. What do you see about that sponge, first off? Oh yeah, good, good, good. So exactly, pores, right? Are they the same size? Much like our soils, right? Because they're a conglomeration of both sand, silt, and clay, plus a lot of organic matter, right? So these are the bigger pores, macropores, smaller ones, micropores, but they're all the same. I mean, they have variations in how they're going to bring water in. So here's our hayfield, and if I'm irrigating, okay, what's happening right now? What's the term? Right on. And then, is it going in fast or slow? Very good. Okay, so that means we have a little bit more bigger macro pores in the soil, right? So as I keep going on this thing, eventually we'll start hitting what they call field capacity. Beforehand, what you have in your hand would be basically, let's say, wilting point, and we'll get into water relations in my next slide. So as we irrigate our hay field here, okay, something's happening on top of this surface. What's happening? And it's hard for you guys to see, but as I irrigate, all of a sudden, it's becoming a little bit more slower going in. Starting to pool, is that what you say? Exactly. Saturation, that's perfect, exactly. Pool, saturation, that's exactly the terminology. So once your thing is at saturation, you start becoming almost at field capacity. Now what's happening at the bottom of the bowl there?
It's leaching.
Exactly. So they were talking about leaching potentials, exactly. So basically what happens is now you're oversaturated or at saturated, you're beyond what they call field capacity, okay? And so what's going to happen and what Abigail and Garrett are going to be talking about are methods how to keep your water from oversaturation, keep it within the profile itself. The other thing that I always like to do, and I'm watching my time because I want to really zip through this. So everybody gets that. Okay, here's my lavender field. And you hit it on the head. Somebody basically said about oversaturation and all. So what happens if all of a sudden, here I am putting my fertilizer down, my 16, 16, 16 that I get from Tim over there at Midstate. And then I just, kick on the irrigation and I go to work and I'm on 11.5-hour sets. That means my irrigation's going on for 11.5 hours on a sandy loam. What do you think's going to happen?
It depends on your application rate.
That's what they're going to get into. Exactly. I'm glad you're hitting that. That's perfect. Exactly. And this is what you want to kind of avoid. Notice how it's now, I'm oversaturating and I ran out of water. But that's what I want you to realize is sometimes 11.5-hour sets may not be, maybe adjustment to your timing, nozzle size, whatever. Exactly, you're right, and that's what they'll get into. So again that's what you want to prevent because that's money down the drain. 2, that's non-point source pollution of leaching potentials either of your fertilizer, maybe it's runoff from the pesticide too that's going down. That's what you want to kind of avoid. Your problem is trying to get the water on as opposed to overwatering. And so it's tricks of the trade of how to do that. And they'll talk about it in a way on how to do that. Now, one thing I do want to do and wrap this up is people always ask in drought situations, what do you do? What are things that, obviously soil amendments, organic matter, composting. What that does, it just adjusts the structure and it adjusts the aggregation of the soil particles. And actually it gives more surface area, more pore spaces. Actually, I've heard everything from about 10,000 times more water holding capacity. In some literatures that I saw was something like 20,000 gallons per acre. That introduction to organic matter and stuff and incorporating. What that does is just increases your surface area, increases the amount of pore space that it can infiltrate in and hold into the soil. Soil relationship, real quick, this is getting down to the end of it, where then I'm going to pass it off because then you start really getting into what you can do and how you can tweak and dial your irrigation. When the soil relationship and water relationship in a soil profile you have your, obviously your soil profile here, and then, or soil particle. As you irrigate, okay, if you over irrigate, this gravitational water is not good for the plant because it can't take it up. It's just there. So you want to minimize your gravitational water. You really want to have your available water because this is where the capillary action works in your plants. So you really want to keep the water in this more available water. And there's tricks of the trade because now you're going to have to talk about ET, you got to talk about crop consumption, you got to talk about how much water your soil can hold. And then if you mismanage and you're not irrigating, this is what's called unavailable water, which is hygroscopic. That's what it's called, hygroscopic. And it's different than hydroscopic, because hydroscopic is a little thing that you have to see in a scope. Hygroscopic means the absorption of water to a clay particle. And that particle, and Garrett said something that was really funny to me yesterday, because it was like, he was telling me about college students and trying to suck up as much of the water from this unavailable hygroscopic area here. And it's like, I think you guys must have taken bets or something, I don't know. But anyway, that's about 15 bars, okay? That's something like 220 pounds per square inch. You cannot pull that water away from this soil particle. You can't do it. Field capacity is somewhere around 4 pounds per square inch, and so that's enough for a plant to uptake it and get the nutrients on. But when you get to this point, that's called wilting point, not good for the plant, not good for the plant. And so what we want to do is minimize the amount of time, or I should say minimize water consumption that won't get you to wilting point, but can actually, you start balancing your water scheduling to make sure that at least you can get enough available water, or maybe 50% or whatever the crop maximum allowable depletion would be. And with that, I am going to quit because that just kind of gives you a real big overview, but how water interacts with the soil. And the next speakers, actually, Garrett and Maria, will get really in depth. So again, pore spaces are the big holes, right? Infiltration, going into the sponge, right? Let's say into the ground. Porosity is the amount of holes, how that water moves. Available water is the water that's just outside that soil particle. Unavailable water, hygroscopic, is where you get it to wilting point, and it just cannot break away from that soil particle.
So now I'm going to talk about the WSU irrigation scheduler, and we're going to do a little tutorial and go through the process using it. And in between, I'm going to kind of address some of the elements of the irrigation scheduling process. We're going to cover 3 elements. We're going to look at crop, water use. We're going to look at soil, look at soil a little more deeply from what Todd just talked about. And then we're going to look at an irrigation system and deciding what the rate is and how to determine how much you should irrigate. So first, I know there's an email we suggested. Encourage people to register for this ahead of time. If you haven't done that, if you would please do that now if you have a smartphone or your computer along. If anyone wants to, this is a scanned QR code. You can come up here and use your camera. Maria showed me how to do that. I was unaware before. But
just open your camera and point at the QR code. It will redirect you to a page that you can create an account so you can follow through all the next activity that we're going to be doing.
so,
So if your phone doesn't pick up like from far, like please come closer and just scan with your camera.
If you don't have a camera, you can use the website right here, but I'd encourage as many people as possible to register now so that we can actually go through the process. And that will give you the tools that you can easily use it again for your own system in the future. So we're gonna walk through that. So I'm just gonna go through a few slides. I know a lot of you are probably still logging in and registering. That's fine, I'll just go through these before we get into the rest of the tutorial. So irrigation water management, why are we doing it? There's a few reasons. Conservation of water, as you all know, drought, limited resource. The energy that it takes to pump water that is not needed, that's excess, that's waste, that energy waste. The nutrients that you lose in your soil and that cause downstream water quality issues. And that goes along with the habitat. I have this graph here showing that irrigated agriculture is 88% of the freshwater use in Oregon. So it could be significant. Every drop counts, and conservation matters. So here's just status. I just pulled this off the NOAA website, showing the last 30 days. It looks like it's not looking too good. Looks like we're under 25% for most of Oregon of usual precipitation. And this is the status of our basin, all the reservoirs. You can see our place is North Unit Irrigation, so I always look at Wiki-Up, but it's 45% full. And you can see the other crescent, they're all looking pretty low right now. This slide is about where farmers usually, this is a survey done in 2003, where farmers usually get their information for agriculture or for irrigating, and mostly it's neighboring farmers, surprisingly, 55%. Yeah, I wonder where those neighbors got their information. So efficient irrigating means when and where. So how long you irrigate, when you irrigate, and also where you get the water. So if you're irrigating too deep and it's below the roots of your plant, if you're germinating like say any plant and it has very shallow roots, then you don't need a deep irrigation.
So we're going to be back and forth trying to explain a few concepts. So when you talk about irrigation scheduling, you need to understand how much water you're going to apply, and then when you want to apply that water. So for that, we need three main concepts. And to do that, you can click on the next. You need to understand what are your crop, what is, as Gerd was explaining, what is the root of that crop and how actually like uptake that water from the roots. Then you need to understand the next one, the soils. What Todd was explaining before, like what is your mineral part of, like what is composed of like the clay, silt, and sand. And then you need to understand like the irrigation systems, how we're going to deliver that water to your plants. So these three main components is going to determine like the total amount of water and the timing that you want to apply. So through different things, we're going to be covering these components, so remember those ones.
All right, so yeah, basically just what she said, when, how much, and how fast. So when you apply it, that's on the calendar. How much, that's a function of your system. And how fast is also your system. And how much is set time as well. So we're going to look at soil information. There's some, how many people have heard of Web Soil Survey? Okay, a few of you, but Web Soil Survey is it's an NRCS program that's been around for a long time, and you can log in there and look in your specific area and see what your soil type is. It's fairly accurate, I would say. Some people, you know, it's not always right, but gives you a general idea of your soil and how much holding capacity. It has all sorts of information in there that you can look up. And then we're going to talk about Agrimet. That's for this app that we're going to go through. That's the weather station. It's for Bureau of Reclamation, this Agrimet stations that provide data that we can use for live weather information. And crop information is also important. So different crops are going to use different amounts of water, and so we'll look at that too. So now if all of you have your, actually before we get into that, I am going to hand out a quiz to you all. So anybody want to say what you got for number one? Okay, anybody else want to say, give an answer? 300 cubic inches. All right, so let's just go through this. So we have 1,000 square inch garden space. So just that's the area of the garden. So we got a garden bed. It's 1,000 square inches. So it's 1,000 square inches, and we know that it uses. So there's preliminary steps here, but we're saying that we know that it uses 0.3 inches per day. So it's using 0.3 inches deep. So that'll be like the depth of application if you imagine a volume of water. And so the reason I want to point this out is the 0.3 inches. I think when I got into this field, first thinking someone would say like 1 inch, I'm going to apply 1 inch of water. And it's like 1 inches, like vertical distance for water. Like I thought water's in gallons, you know? So that's what this is here to illustrate. So 0.3 inches, that's actually, you can look at that as a volume per square inch. So it's a volume per area, and we just say 0.3 inches applied to this area. When we have a specific area, 1,000 square inches, we can actually calculate a volume. In this case, 1,000 divided by 0.3, that's, I remember from math class, you move over the decimal place 3 times, 1, 2, 3, so that's 300 cubic inches. So that's the answer to that, 300 cubic inches. So any takers on the second part of that?
Well, that's why I'm not an
No.
engineer.
1.3, anybody else? Anybody else get that? All right, so that's 1.3 gallon. There's a conversion to convert to gallons. So now I'm gonna give you guys a few more minutes to go through number 2 and 3. So number 2A. So now we're saying, we're gonna imagine this as the garden bed here. And we're pretending it's 1,000 square inches. And it has a depth of 15 inches, which anybody know how many inches they have in their fields where they're at? Like, I've seen a lot of 15 inches around.
Yeah, we like 15 inches all over.
So we got 15 inches here on our garden bed, and so this available water holding capacity is 0.12 inches per inch. So that's like saying that 12% of the soil can be water. It can hold 12% of its depth can be held as water. So let's do that. So we got 15 inches deep. Actually, before I do that, does anybody come up with the answer for that? For how many inches of available water can that soil hold? So it's 15 inches and it holds 12% of that can be water. 1.8. Anybody else get that? Yeah.
Yeah, you're just looking at that 1 square inch or the whole garden bed.
So good question. Are we looking at the whole garden bed, or are we looking at just 1 square inch? Depending on how big the volume will change depending on how big your area that you're looking at. So it is looking at, that would be the amount of cubic inches per 1 square inch of area.
15 inches deep.
15 inches deep. Yeah, 1 square inch of area, 15 inches deep. It'll be 1.8 cubic inches. And when we say 1 inch, that's meaning per area. So it just depends on what what big of area it is for the actual volume.
So if you imagine whatever area you're talking about, an acre or your 1,000 square inches, if you kind of pretend you pull all that water out of the soil, it would be the amount of water that would cover that area to a depth of 1.8 inches. So it sort of scales. You don't have to think about how it scales to area, but it's that. Think of it as just a depth. If you covered it in 1.8 inches of water and let it soak in, that's how much water is in that profile.
Exactly, yeah, that's a great way to put it, yep. And so did anybody, for number 2, how many gallons is that for this garden bed here? What's that? 1,800. Okay, got 1,800, 7 point, what'd you get? 7.79 gallons. All right, anybody else get that? You got that? Any other answers? All right, so you can see to convert this right here that, let's see, 1.8. So I'll start over here. So 1.8 inches, we're going to multiply that by the 1,000 square inches. So we got 1 inch, like a depth, like you said, of 1.8 inches. So it's about that much over the whole garden bed. And how many gallons is that going to be? So we're just going to calculate the 1,000 square inches by 1.8 inch to get the 1.8, which we got before. And then to convert it to gallons, that's 231 square inches per gallon. And that comes out to, yeah, 7.8 gallons. So 7.79, rounded it to 7.8. Okay, part B. So if the lettuce can deplete no more than 25% of the soil's water before being stressed. So what we call that is the available of the maximum allowed depletion. So lettuce only lets use 25% of its water before it gets stressed. How many inches of water is available to the lettuce? Anybody, any takers on that one? So we said that we have 1.8 inch. 1.8 inch is available in the soil that regardless of how big your garden bed is, we know it's 1.8 inch. And we know only 25% of that is available to lettuce before it's stressed. So just going to multiply that by 25%, and that's 0.45 inches. So yeah, something to keep in mind when you're irrigating is we only want to apply 0.45 inches and only let it get depleted to that 0.45 inch. And for this garden bed, how many gallons is that? So then that's, we're going to multiply because we're doing a specific area, 0.45 inches multiplied by 1,000 square inches. And that comes out to 450 cubic inches. Convert that to gallons, we get 1.9 gallons. Anybody else get that? Yeah. All right, and so now we're looking at the lettuce. We know, because we checked our weather stations, we know this day it's going to consume 0.3 inches. And we're wondering how long is it going to take for the lettuce to use this water, this 1.9 gallons that we applied, how long is it going to last? So we take this 0.45 inches here. Well, let's see, anybody come up with how long the water is going to last? Day and a half. Nice. 0.45 inches times a day, so 0.3 inches per day. We divide that, we divide 0.45 divided by 0.3, we get 1.5 days. So yeah, it's a lot different from pasture. Yeah. So how many inches per hour are delivered to this garden bed? 15 emitters at 0.2 gallons per hour. How many gallons per hour is that? So that's some arithmetic. 15 emitters times 0.2 gallons per hour comes out with 3 gallons per hour. So that's how much we're putting on. That's like the flow rate that we're putting on. And what we're interested for this planning, because is not for this specific bed, but we want to know a rate that can be applied to any area. We want to know the inches per hour. So we can convert that. 3 gallons per hour. First let's convert it to cubic inches per hour. And that's 693 cubic inches per hour. And then for this specific bed, we know it's 1,000 square inches. So we divide by that. Cubic inches per hour divided by 1,000 square inches. And that comes out to, anybody get this one? What'd you get? How many inches per hour here? I got 0.69 inches per hour. You got another one? Got that? That's good. Yeah, I'll go through it again. Hang on. So we got 15 emitters at 0.2 gallons per hour. You got that part. That's 3 gallons per hour. That's the rate of the system. Converting it, we have the conversion factor, 231 cubic inches per gallon. So I'm going to just say 3 gallons per hour and divide by, or multiply by 231 square inches per each gallon.
There you go.
And then so I can cancel out the gallons, and then that ends up being 693 cubic inches per hour.
Got it. That's what I thought.
So that's a volume rate, but we want to convert it to linear distance per hour, so inches per hour. So we're going to look at what our specific area is here. And 693 cubic inches per hour divided by 1,000 square inches equals 0.69 inches per hour. Any questions? Yeah.
So how would you do that equation if, say, you were working with an acre?
An acre? Right. Yeah, for an acre. So we would be looking at our total flow rate for the whole property. If you're irrigating an acre, like what's your flow rate? How many gallons per minute? In this case, it would probably be not gallons per hour. It'd be, a different unit, gallons per minute. And then we'll do the same method by taking your volume rate, so volume over time, whether it's in gallons per minute or what it is, and multiply that by, or divide that by your area.
So an acre is just another way of saying the surface area, right?
Yes.
You just look up the equation for an acre equals this many, say, meters squared, and then you convert it that.
Yeah.
So it's more just like it's one unit for the whole area.
We can convert that unit. So an acre is 43,560 square feet. So then the last one, if 25% of the available water content is depleted, which we calculated already, it's 0.45 inches is depleted. How long should the drip system be left on to fill that? So it's depleted to its maximum, 0.45 inches, and our bed, 0.45 inches of water, which is, it takes up more than 0.45 inches in the soil because it disperses throughout the 15 inches. But it's equivalent, if we were to take all that water out and put it on the surface, it would only be 0.45 inches of water. And how long is that going to take? So now we know that we're applying it at the rate of 0.69 inches per hour. And so every hour it's putting 0.69 inches on, and we have 0.45 inches that are depleted. So it's gonna be less than an hour, right? 0.45 inches. It's not very. And then we'll multiply that by an hour over 0.69. So I'm basically dividing that by 0.69 inches per hour. Anybody, anybody get an answer for that one? 0.65 hours, which we can convert to 39 minutes.
Is there an app for people that are math challenged?
So I'm going to show you how to use it on WSU app, as long as we have enough time. And that's going to show you, it'll walk you through these steps to some degree. But it's important to know the fundamentals of it so you don't make a big mistake using the app and put on way too much water. So that's why we went through this. All right, so if you guys have your app and you want to pull it up and click on the Add Field button. And then I'm going to walk you through getting this set up for this field. We're going to do lettuce, and you can go along with it. So, and then there's a button that says Add New Field. Does everyone find that? So in the Add New Field, let's put in for the year. You can name it whatever you want. I just call it garden example. We're going to go through the same setup, and then later you can do this for your own field. But let's put year 2021, because we put 2022. It's not the growing season yet, so the data isn't going to be there for us. So we can actually use the previous year and go through the example with that. So put in 2021. And then you'll select a network. And then we're going to choose Agrimet. You can see that that's where there's stations in Oregon. And then on the next, there's a station that you choose. So you can use Pal Butte. If you want to use a different one, I think that's fine. We might come a different answer, but I use Pal Butte. There's also one in Bend. Bend and Pal Butte, I think, is like the closest ones to this area. All right, and then the next column, there's this crop, and then we'll go through and select lettuce for your crop. You can see that there's all sorts of different crops in there. All right, does everyone get through that? All right, and then look at the soil. I select sandy loam. That's very common in Central Oregon, but it has all sorts of options if you know, and that's where what Todd was talking about. You want to feel your soil and know how to identify it, or use the web soil survey. All right. So we got lettuce, sandy loam, Pal Butte, weather station. And then at the end, make sure you hit the Add Field button at the bottom. If you don't hit that, it doesn't save your information. All right. So you take a minute to go through that. Someone next to you might have the answer. So I'm going to talk about evapotranspiration. Everybody heard of that term, evapotranspiration? Okay, it's basically a combination of evaporation on your field and transpiration, which is the moisture that your plant lets off. So it's basically how much water your plant uses, and we just abbreviate it, say ET. And it varies seasonally. The temperature affects that. Humidity, wind speed, all these things affect how much, as kind of common sense, how much water your plant uses, depending on how hot it is. And also the growth stage of the plant matters too. So the seedlings, they're really small, are going to use a different amount. And when a plant is like budding and flowering, it's going to use more than, or a different amount than at other times. See here a graph showing the different stage. This is based on temperature and climate considerations, what a plant would use, but it's less at its beginning stage, you see, of corn, and then at the end stage, it's going to use less water as well. So the Agrimet weather stations, it's Bureau of Reclamation funded. There are all these weather stations, and you can see where they're at: Bend, Pal Butte, Madras, and they're all over Christmas Valley, looks like there's one. Oops. So Agrimet has they store the data on there. If you go on the website and you want to really dive into it, you can look at the weather station information and all that. Like I said before, it collects all the weather parameters listed here. Most of them affect how much water your plant is going to use. So here's a graph just showing with most people when they irrigate, or when you like I'm an engineer, I design systems for people for irrigating, and we design based on the most water needed, like the hottest time of the year. If you're going to water the way that you do at the hottest time of the year all year, and you're just going to water the same way, you're going to waste a lot of water in the spring and fall because the temperature is not warm and you're not using as much water. So yep, those are the excesses there. All right, so the next step, now that we've added a field, is go in and you'll see a field settings button. And this is the first one I like to go through because it sets a default in there. All right, sorry, yeah, field settings, and then we're going to click on season date settings. And I like to go through this because it sets a default. You see here for lettuce, it's suggesting that we're going to plant our seed in April 5th, and it's going to be at 10% on the 6th, the next day, and then 70% by the 20th of April, and then you're going to harvest it in May 5th. So that may or may not be what you're doing. So you want to adjust that right there.
Would you say planting on that day and then?
Yeah, so it shows the emergent. Well, maybe it's not planting, but it's the emergence. So maybe it's, yeah, a few days before how
Does that automatically change the canopy cover as your year go, or do you need to do it every time you look at it?
Like when
it has default values, but you can modify those values.
Does that answer your question?
Like as you see observations in your field, you can adjust them. So you can adjust your water use too.
Yeah, so we need to adjust the canopy cover.
It would default.
Oh, based on, I see what you're seeing. Based on what you actually observe.
Right.
You could, I guess. Yeah, you could do that. I think the general, yeah, I don't know. Maybe you could adjust it once you see that it's to 10%, or more likely just what's expected for that plant. Just put that date in there, what maybe the seed packet says or something like that. Just put in that date.
If you're using plastic mulch, you could put like 100% or 95% on there.
Oh, okay. Oh, I see what you mean. No, so this is just greater than 70%. So you put the date that it's greater, and then that's it. So you don't have to change the 70%. Does that answer your question? Yeah, transplants, that's a good question. I think I would just adjust these dates so that there's pretty much no time. Maybe you could have these dates as the same if it lets you. If you put in at 70% already, then maybe just jump to that point there and just say April 5th, April 5th, April 5th, if that's the day that you transplant them. Yeah, that's what I would try to do. If it doesn't let you, then maybe do the next day or something.
Or you can estimate like what would you expect earlier, because it would just try to develop the crop water use first.
Oh, that's true.
I don't know if having the same date is going to be, it's going to make an error in the calculation.
Yeah.
And if you just said, okay, when you plant it, it will be your canopy cover at 10%.
And I'll show you when you go on. If what happens before doesn't matter so much, because you can get in there and edit the soil moisture, and I'll show you that in a bit. So yeah, as long as you're putting the date that you're putting it in for here, from there forward, I think is what matters, if that makes sense. So everybody was able to see that. You don't need to, you can change it if you want or not. We can leave it default and just look at that time period. Any other questions on that part, season date? Okay, the crop settings is the next one I like to go to. So in the settings menu, there's a crop settings button. Let's click on that one. And this one's important because this is where you adjust your root depth, which may be limited by your soil depth. Especially in Central Oregon, yeah, we have some shallow soil some places, 15 inches. I think the default that it puts in here is like, what is it, like 32 inches, or what are you all seeing?
18.
Oh, it's showing, is that what the default is showing when you? Oh, okay. So, but if you have 15-inch soil profile, then you may want to adjust that, change that to 15 inches, because you're not really going to be irrigating for 18 inches if you have bedrock at 15 inch. And then your starting root depth is for when, before it's reached maturation, you'll have smaller, and these are default put in there, but if you know better and you should change it, go ahead and do that. And then right here's these coefficients here. You probably don't have to deal with it. They put default for that plant that could be accurate. There may be a plant though, you have a special variety of lettuce that isn't in there and you want to get it like really fine-tuned, then you know, you may adjust this if you know, but initially I would just leave those defaults in there. That just tells you that it's going to use less water at the beginning and at the beginning of planting, and then later as it matures, it's going to use more and so on.
One thing to note about the app is there's really good defaults for different crops, so if you want to, you can leave them be, but since we are talking about drought management, if you really want to dial in and know how much water you should apply for the conditions, then you can go in and adjust these values.
Right.
Yep. So how is y'all able to set the crop settings there? All right, so jump to soil settings. And so here's where you adjust your available water holding capacity. So we talked about that. This isn't a different unit from the example we did. In the example we did, I said inches, 0.12 inches per inch, I think it was. Here it's inches per foot. So it's same thing, different unit. Julianne?
I have a question. So how would you determine what your available water holding capacity is for your field?
Good question, Julianne. So there's a few methods you can measure it.
What was the question?
So the question was, how would you determine what your available water holding capacity is for your soil? There's ways to measure it. I'm not expert in that, but you can also go onto Web Soil Survey and look at your area, and it'll tell you how much water holding capacity for your specific soil type that you have there. Yeah, and I'm going to go over that, but it's called Web Soil Survey. It's an online resource that you can go in and look at your specific location on a map, and then identify what type of soil you have. And there's a lot of information about that soil, and some of the information you can get in there is your available water holding capacity. So another important one that you'll see as a default is your maximum allowed depletion. You realize in the example we talked about the 25% for lettuce. Grass, I think the default in here is like 55%. So it doesn't have to be watered as regularly. Lettuce has to be watered more regularly, and it can't be stressed as much. So it only has a 25% allowed depletion. So if you know that this is different, or you know maybe a certain variety of lettuce does better with only 20% depletion or something like that, then you can adjust this here if need be. But otherwise, I would just leave it. If you don't, just leave it as is. The defaults seem to be like well thought out. All right, so I'm just jumping through soil again here a little bit. What makes good agricultural soil? We talked about different soil types have different size particles. Sand has like large particles. Silt has small like disc-shaped particles, and clay has really tiny disc-shaped particles, and they hold water differently. The silts and clays are going to hold more water, and they're not going to allow infiltration to happen as fast, whereas sands will hold less water, but they allow infiltration very quickly. And just, yeah, kind of what we talked about before, infiltration. and the wicking capacity, clay is going to spread out more in clay because of the forces in the soil that are going to, it has a lot of surface area on the particles, so it's going to spread out more, whereas sand is just going to go straight. You may have noticed that if you tried drip irrigation like sand, it's going to have wet spots and it's not going to, whereas if you have clay soils or you have a lot of humus, it's going to get everything wet, it's going to spread out better. Okay, so now we're going to talk about the irrigation systems, and the next step we're going to go to the app as well to show that.
So when we talk about irrigation systems and how we're going to deliver the water to the plants, we have been talking about different terminologies, but I want to make sure that everybody has a clear understanding of these terminologies. And what I want to point out here is, like, we're going to imagine that our soil here is like a bucket that we're going to be controlling water. And this is our top part of the bucket. And for example, we have a sensor over here. We want to measure like how much moisture is in the soil. So field capacity is what Todd explained here, that amount of water that the soil can actually hold without draining. So we're not going above this point, and the plants are actually capable of absorbing that capillary water around the porous media. So the permanent wilting point is kind of like our bottom of the bucket, and is pretty much water that is very is held like really tight to the particles, like to your soil, that the plants are not capable of taking. So this is water that we don't want to get here, because once we reach to permanent wilting point, as it says, it's wilting point, we're just kind of like the point of no return. It's really hard for plants to get there. So we have this maximum allowable depletion, or this kind of like sweet middle point, and this is like the amount of water that we're going to allow the water to be depleted from the soil. And for irrigation purposes, we want to keep field capacity, like the water available for these plants, in this more effective root zone here, and we want to keep water from this point, not above it, because we're going to be losing it through gravitational, it's going to be gravitational water or percolation, and these other sweet middle point that is like the maximum allowable depletion.
I want to point out that, like in lettuce that I said 25% we put into the app is the maximum allowed depletion. So that's of the field capacity water to the wilting point. So that water right here, this looks like about 50%, but for the lettuce, it's only 25% of your water in your bucket that you want to use. Mm-hmm. Go ahead.
Yeah, perfect, exactly. So that means that the lettuce is much more sensitive to water stress, because you want to apply water more frequently, and you want to keep water like not too much, because you don't have huge roots to actually reach to that water, but it's stress enough, so it's more water stress, so you want to keep it like in more frequent applications. So what happens in general is that evapotranspiration occurs, so like water is being depleted, and we were here like at field capacity, now we're here. But let's say we're in Corvallis, so then actually we have rain. Not necessarily over here, but like, let's say we're over there. So our water capacity went from this maximum allowable depletion, and it's within this zone. So we don't necessarily have to irrigate. We have enough water around the soil material that is available for the plants to actually uptake. But then the next day, we are here, and evapotranspiration occur, and we reach to this maximum allowable depletion. So if we don't have rain, because we know that it's not going to rain today or tomorrow, then we have to really apply irrigation and replenish this amount and go back to full capacity. So those are important terminologies that we want to keep in mind when irrigating.
So now this is basically a refresher of a just different form of what she just was talking about, but this graph right here shows different soil types and the different available water that you have. You can see in sandy soil, that you can't hold much water. So this water down here, the unavailable water, we don't even have to really think about because it's in the soil. And I mean, you do have, if it's completely dry, you may need to fill that first, but that's available, that's not available to the crop. So we can, as long as we're up to the wilting point, we don't have to consider that. But you look at sandy soil, you see that the available water is very small. So with sand, or with lettuce, we're only going to allow 25% depletion of that. So that's 25% of that available water. Whereas if you have a really clay soil, you have a much larger, the distance from here to here, amount of water available that you can deplete. So you're going to have to irrigate more regularly, more often in sandy soils than clay soil, for example. Go ahead.
I have a question. So we need to know how much our soil will hold, but we also need to know what's available for the plant. It seems like to me.
It is. And so that number that we talked about, the available water holding capacity, that's only looking at this available water.
Okay.
And so
that
web soil survey,
yeah.
Yep, the data that you get, it's only looking at this available water. It's not considering this unavailable water. So that's just kind of, if you hadn't irrigated in a very, very long time and you're completely bone dry, then you're maybe gonna have to add more water to get it up to the available level because you have that initial water just to fill the unavailable part.
One way you can think about this is if you're like drinking from a straw and you have like a really thick milkshake, right? You have to like suck really hard in order to get when it's thicker out. And so think about it if you have a plant root and it's trying to pull from that really tight clay soil, it takes a lot more suction, a lot more force for that plant to uptake that water. Which is then when you look at, so from the sand to the clay, why that goes up and there's more unavailable water for the clay. Does that make sense?
Yeah, cool. I like that analogy. Thanks. Okay, here is different available water holding capacity. So that value that you put in there, it's different for different soils. So gravel and cobble holds less water than, like down here at the bottom, we got clay soils. There's more available water for clay soils. And you can see the range there. We're at sandy loam. We put in 1.3, I think. So we were right in this area here. So we saw that before. So this is specific soils to Central Oregon that you can see here. And these are kind of estimates. I've been told recently that this specific numbers may not be so accurate. So I would check web soil survey to get those numbers. But just so you know, there's different values for different soils in Central Oregon specifically. This is web soil survey that I was mentioning. It's websoilsurvey.gov, I think. If you Google it, it'll come up, and you can, if you have questions about how to use this, contact your NRCS office. We can walk you through the process. There's a lot of information on there, and it takes a little bit of learning, but it's not too challenging. So you select an area of interest, and then it identifies the soils. You see the numbers for the different soil types in this area. You click on Soil Data Explorer, and then you create a soil report, and then you look at physical soil properties, and it'll give you this information. You see this one column here, available water holding capacity. It gives you inches per inch. So that's where we use an example, that unit. And you can see for all the different soils at different depths, it gives you a different water holding capacity. So this is inches per inch. We just took an average for a soil and just said 0.12 inches. And you can see that's pretty close to this specific soil, 0.12 inches per inch. So this could be a Deschutes soil. So I just want to point out the effective rooting depth, that there is Most of the water that your plant takes is near the surface, and then it's lesser important to the water that's lower. So it uses that water, but not as much as it relies on the water closer to the surface. So the root zone depends on the crop as well. Alfalfa can be down to 4 feet deep roots, whereas another plant like beans, it's 2.5 feet. Lettuce, we realize it's much shallower, 18 inches I think was the default. All right, so back to the app. Now we can go into general settings. So this is where we're going to set up our irrigation system for this lettuce garden that we have here. So if you go into settings and click on general settings there, and there is this button here, help calculate my application rate, which we're going to do, and that's going to help us know what our rate is in inches per hour. We just did it by hand for that drip system with lettuce, but I'm going to show you how this tool is helpful in that it will walk you through the steps and it will calculate it for you. So yeah, so click the box that says use hours, then press the help calculate my system, and then you'll see in there that there's irrigation type, there's a drop-down menu. You could select your type. I think they have all sorts of sprinkler systems or systems for irrigating in there. So for our case, we're going to look at lettuce. We can click on drip, and just like we did in the example, let's say that our emitter flow rate is 0.2 gallons per hour, and the emitter line spacing, you see on the drip line, they're spaced, the holes are spaced on there. That's what that's referring to. When it's talking about the 6 inches, 6 inches is the closest together, I think, on there, but can also do 9 or. How did you get that? There you go. Yep, you got to click the help calculate my application rate for this, and then it gives you all these other options. So. Good. Okay, and then yeah, the drip tape that you get, it has a flow rate. It's usually dependent on like 15 psi, something to keep in mind. If you don't have pressure regulators on your drip tape, you may be putting out more water. But the manufacturer tells you how much it's rated for the flow rate. So 0.2 gallons per hour. Put in your spacing, 6 inches, and then distance between each drip line. Imagine this is like longer, the spacing in between them. Each drip line is, I put in 1 foot, and then it defaults like application efficiency at 97%. So if you know better about the efficiency, you can adjust that. Otherwise, I would keep the default.
How much water gets to the ground?
The efficiency? Yeah, it's how much water actually gets to the roots versus evaporation or leaks or other losses. And then you hit calculate rate at the bottom, and then it will calculate your rate. So if you did exactly like I did here, it comes out about 0.62 inches per hour. So with that set up in this box checked, use hours instead of inches, in a second I'm going to show you the budget, and it's going to tell you how many hours you need to irrigate. Otherwise, it'll tell you how many inches you need to irrigate. So it's a preference. If you know, like people with a sophisticated like pivot system, they can just put in like 1 inch and it'll just put on 1 inch. But if you're based on time, you may like the hours, because then you know how long you need to irrigate. Okay, so now we got it all set up. Now we can look at the actual system and how it shows you when to irrigate. So if we go down at the bottom and click on the daily budget table. So it's like a budget, like your checkbook, how much water is going in, how much is going out. And you'll see there's dates on there, and you can adjust what date you're looking at. I went into when we were planting, when the emergence was happening, so 4 or 5, and all this information gets filled in based on the ET data and the soil parameters that you put in there. So I think mine, I'm curious what your guys shows. Mine showed on 4 or 5, it had 100% of water, suggesting that there was actually rainfall event in 2020, in the beginning of April, that filled the soil profile before that, or snow melt. And nope, what does your guys show?
I know April 11th, we were dry.
For last year? Maybe that's not a good example that, that may be wrong then. So I would check the weather station. If that was the Bend weather station or Powell Butte, then I would question that. But this does give you the option to adjust that. So if you click on this button right here, Edit, you're actually able to change the water that's available water. So you can actually measure it with soil moisture sensors that we may be able to discuss, and you can actually override this 100% and put what your actual moisture is. And then you can see right here, it's how much the plant is using that day. So 0.12 inches on the 6th and so on. Right over here in this column, water deficit, it shows you how many hours of deficit you have. So when it's in red, it means you need to add more water. 0.4 hours is how much you need to irrigate in order to get it to full capacity. You can see you're down at 69%. So what I did is I went in here, hit edit, put in your hours, 0.4 hours. I did a virtual irrigation season, went in here and changed and irrigated exactly when I was supposed to, and shows everything is green.
So does this work for wheel lines and stuff like that? You're not covering your whole field at the same time?
Yeah.
You're doing a strip of field side, and you don't have to dig into the cut. I just want to know if it works. Maybe that's one of the options, so you know how often you need to.
Yeah. You can put your schedule on there. Yeah, so in that case, if you have a wheel line, you do like 11.5-hour set, or maybe an 11-hour set. And so you'd put those hours in here, and then you can keep an eye on that during your irrigation season, depending on your schedule, and you can see what your moisture is in your soil.
So when I click edit, it looks like your screenshots there, except for irrigation, when I input it, it has it in units of inches instead of hours. Okay. So on that previous step, if you go back into general settings, there's this button right here that you got to push to change that. So if you hit that, it'll use hours instead of inches. Oh, there you go. Yeah, I should have pointed that out. Update field, these buttons you got to press, otherwise it won't save it. Yep, good point. So does everybody see how to enter in your irrigations? See how that works? Great. There's also, in that, when you hit edit, you see reset correct percent available water content. You select that. That's when it gives you the option to override and to change what your water content is in the soil for that day. So you go out, you measure it, and you say, oh, it's a little different from what it says. You can update it, put in there. So yeah, I think this can be helpful to keep track of your irrigation, and put in your system. If anyone has any questions, feel free to reach out. I'm at NRCS office in Redmond here, and there'll be other, reach out to me there, and I could assist you with this. Another option that it has at the end, you can click soil water chart, and it'll give you an actual graphic of your water content. You see the available water when your root depth is really shallow is really low, and then as your roots increase, you have a larger available water capacity. And then the red line there indicates the maximum allowed depletion, and you can see how do you think I did on irrigating there? All right?
Really good.
Yeah. There's one spot you can see right here. It looks like I over irrigated a little bit. Came up and I over irrigated, so that water that I must have went in there was lost. But yeah, it's pretty good. You see here, this shows my irrigations with the green dot.
That's the point when I irrigated.
How much water you put down?
Well, it's not how much, well, yeah, it is. Yeah, it's how much water I put down for each of those days, correct, yep. And then there's also the blue, and those are the rain events. So yeah, it was pretty dry until, looks like the end of April. That didn't get any rain.
Even if you guys don't use this to irrigate exactly, it might be interesting just to put in your crop, put in your parameters, and compare it to how much you're irrigating at the moment.
Yeah.
If there's any discrepancies.
Absolutely. All right, so that's any questions? Yeah, Anna. Yeah.
You want to be using NIFA and learn to then update it and fill in the second as well once it's done changed. Is there any latency on the climate data coming in? Like,
I think it's live. I don't know, at the end of the day. I'm not sure exactly how often it goes in. And it also forecasts the future weather as well. And so you can look into the future and estimate when you need to irrigate. So I didn't mention it here, but there's also an option on there. It didn't work for 2021, but when you do it for live, it has like on the dashboard you click on, and it tells you, it gives you this little speedometer and tells you irrigate now, and kind of, and there's options to have it text you and tell you when you need to irrigate and that kind of thing too. Does that answer your question? Kind of, yeah. Any other questions, or move on to Maria here? Thanks. Thanks. Thanks.
We're going to move and switch gears a little bit, and we're going to talk about some of the strategies and some reminders or refreshers of what you can do when you have like limited water supply. And through the presentation, I'm going to go over some of the challenges that we are facing in the Pacific Northwest, as well as some actions that you can take to improve crop water use efficiency. And then I think we have seen a lot of math today, and we're going to probably skip this part. And I was going to go over runtime and irrigation cycle calculations, but that is, it was going to be like step by step. And I think Garrett already covered pretty well, but if you guys are really interested into that, like, I can actually go and explain you a little bit more. We're going to squeeze a little bit some other topics on irrigation scheduling using soil moisture sensors and tensiometers that Abigail is going to cover too. So in terms of the challenges, the drought in the Pacific Northwest has been classified as a spring drought, and 2021 was one of the, it was the second driest March since 1924, which is put like 52% of the Westland was classified, as you can see over here, into extremely, or it was experiencing like extreme or exceptionally drought since the past droughts in the 2000s. It is actually called the spring drought because it's a failure during that springtime of precipitation to actually boost high levels of snowpack and runoff, which had led the entire region to experience a lot of like early fire seasons. The reservoirs had been depleted, as Garrett mentioned before, to really meet the crop water demands and other demands due to all these also summer heat waves. So there's some consequences. A lot of water supplies have been cut or limited around in different parts of the state. And these due to the drought conditions, but also due to the stream flow depletions. So a lot of questions, right? How much water can I apply this year? How much land should I irrigate? Which crops should I irrigate? How much profit can I expect? Some of the questions that a lot of people have been asking themselves, and it really depends on where you are and what your capabilities. So it's not like a straight answer that you can do, but there's some things that you can do and actions that you can take over when you have limited water supply. There's also like new technologies and new things that can help you with those decisions. So really, we want to increase the efficiency of the water and the nutrients. So that means that we want to minimize any kind of runoff like leaching or environmental impacts. these new technologies or new systems, you can, let's say if you have a pivot, you can transition into a much more efficient irrigation systems to really put the water where it needed. The plant can't uptake it. And that is going to increase also overall agricultural productivity, and it's going to optimize that amount of water that is available to your plants. As we mentioned before, like the evapotranspiration is these two main processes, right? Like the evaporation from the soil here and then the transpiration from the plants. When we are talking about improving efficiency, we want to make sure that any losses, or also like the leaf interception, because we have water when we apply it over the canopy that is actually in the canopy and it's evaporated from the canopy. So it doesn't actually even reach the soil. So when we want to improve any efficiency, that means that any kind of water, we want to focus it on this part, the transpiration part. So that is water that is going to be available in the root zone that the plants can uptake, and it's going to go through the xylem, it's going to go and help them do photosynthesis, and then in terms of the plant, they're going to create carbohydrates to grow and to actually put it into yield. So we want to minimize any losses here, this evaporation or this leaf interception where it's in the canopy. We saw this before, and these are like the three major concepts that we are going to be working on, like really understand your soil, really understand your crop and your irrigation systems to determine how much water to apply and the timing to apply. So the exercise that we went with Garrett was very useful because that could be a tool that you can implement in terms of determining how much water you need to apply for the plant, not excessive water. And that tool is accessible for everybody. You just have to create an account, and it's free. So get familiarized with that, and that is going to help you with like the calculations that were a little tough. But after, once you have a tool, like it's good to get familiarized and then corroborate with your own calculations and determine how much water you need to apply. We saw all this before. We really want to focus on like how much water we can hold to and make it available for the plants. When we are focusing on the crop, we want to make sure that early in the season, for example, we have a very small plant that is not going to require much water. But as this plant grows and starts creating more carbohydrates, it's going to put those carbohydrates into the biomass, and it's going to grow into maturity, even reproductive stages. It's going to flower, it's going to create a new seed or a new, it's going to put the yields on. So as it progresses, we have to think about how much water is actually uptaken, but it's not necessarily the same amount of water here than in here. And it's going to influence by all these parameters, like weather parameters, like how much sun is receiving, how much wind is actually like evaporating from the soil, how much humidity. All those weather parameters are going to influence into how much that plant is actually pulling out of the soil. And also, it's important to remember like that all these roots, even if they can go way down here, not necessarily all of them are really effective. So you really want to manage for the effective root zone, which is in general like half of your entire root zone. And another thing to remember is that depending on your crop, maybe you cannot see this, but like over here, this architecture of the roots are completely different from a shallow rooted system. So a plant like this is never going to reach water down here, but a plant like this is going to reach there. So just be mindful of those things and be careful. And sometimes the easy way to measure this is like get a shovel and check where are your roots. Sometimes whenever you don't see it, you don't know how far they go. So I would suggest like just do a hole and try to see where the roots are and where is your moisture to going. So we go over this, I explained before. So I just want to remind you about that we want to keep irrigation with these two main points, the fill capacity and maximal allowable depletion. And we think about this as a bucket that we were going to be like manipulating with irrigation. So when we talk about irrigation systems, we want to make sure that we have like how are we actually delivering that water, and that's going to be your application rate. And as Todd explained before, he was explaining about this hygroscopic water. So that's the water that is so held like so tight in your particles that is not available for your plants. So you want to keep water in this capillary water here, like that is available, but it's not like here that is lost. And pretty much when it's lost, you're losing also nutrients and is bad for the environment. Some important concepts, like just think like a bucket that you want to keep filling in and just allowing that water to go only until you don't see like stresses in the plant. So some of the actions that you can take in terms of improving water use efficiency is really schedule irrigation. So you have two different types of irrigation scheduling. You can use ET based, so that means, for example, using the weather data from Agrimet stations, or these tool that we went through, the irrigation scheduler mobile. So you can do that. There's new upcoming tools that we want to make it available for Oregon, and I'm working on a grant to get that. It's called Crop Manage, and if you guys are interested, you can also look it up. And also there is satellite data that we would like to incorporate into that, and it's called OpenET. The other way to schedule irrigation is using the soil moisture sensors. So you have like two different types, and Abigail is going to cover that, so I'm not going to go into those details. Some other actions that you can take are, and I'm going to go over some of these ones, but you can do deficit irrigation. So that means focusing on only certain stages of the crop. You can do cover crops and conservation till. So pretty much we're focusing on reducing this part, like the evaporation part. Once you cover it, you can incorporate it and you increase moisture in your soil, and that is going to be available for your cash crop, let's say. So it's going to be beneficial for your crop, and you can improve the quality of your soil in that way too. Then simple actions like selecting the proper sprinkler package and making sure that it's uniform. Sometimes we don't focus on that because we just install an irrigation system and we walk away. Just understanding that this part is really important because that is how we're delivering the water, and how much water we're delivering in that particular plant is important. And how we're applying it through the field, that uniformity is also important. And for example, if you have a pivot and you want to upgrade to a much more efficient system, you can use, for example, the LISA system that is pretty much the lower elevation sprinkler applications. Pretty much sounds fancy, but it's not. So just put in like the water where the plants need it, lowering your sprinkler systems to the ground and at very low pressure. So you can increase your efficiency, reduce like the wind drift, and pretty much apply the water and make it available for the plants in a much easier way. So it's a win-win for everybody. And another way is really plan the acreage under irrigation. Sometimes we think that, okay, we have 100 acres. When you have limited water supply, it will be much easier and much better for you to reduce the amount of acreages that you're going to be planting instead of like spreading all across. And this will also depend on the crop that you're going to be planting. But in general, it's much better quality onto quantity. And you can really focus on a combination of like, focus on the high value crops and also on the plants that require less water. And that will require some research because sometimes we have to understand how much that crop needs to really understand if we have the capacity to irrigate the plant. We went over this a little bit too, like the uniformity. Like it's really important how we're gonna apply water through the field. If you have, for example, like low pressure in one field or another, you cannot really be efficient, and we're increasing like our irrigation efficiency. That's the whole entire point. You cannot be efficient if your irrigation system is not uniform. So what happens, for example, if you have lower pressure in one sections of the plant of the field and another ones, you're going to have some of these problems. You're going to see a plant that is dying, and you're going to see if this, what is the cost. And if you think that it's because lower pressure or something, we tend to do this. So that's what, like, it's under irrigated, right? We think, okay, we're not applying enough water. In order to compensate that, we tend to apply water in the entire field. And in general, like, what happens is that you're going to have over irrigation over some places of the field. So it's important to really make sure that you have a good pressured system, that you're applying water uniformly. You can do drip compensation emitters, or you can have pressure regulators in your center pivot too. Because if not, you're going to have, like those variations in pressure are going to cause also non-uniform applications. And then you're going to be not efficient. Pretty much you're going to be losing water here and nutrients and money. So that's important. Maintenance, like sometimes when we would just install the irrigation system, or maybe it's like so many years old and we think that it's going to perform exactly the same as when we bought it. No, it's important to go back and check on your system. So this is pretty bad. Leaks, like a leak is a big amount of water, and sometimes we see a lot of leaks in one single irrigation system. Just take some time during the winter or the spring to fix your leaks, replace all those nozzles, sprinklers, the gaskets. So how much water do you think it's in here? We're losing water there. It's quite a lot. So a nozzle in a wheel line, for example, it's like 5 gallons per minute. But in that leak, if you go and measure it with a can and try to understand how much water you're losing, you're doing 17 gallons per minute. So that's like a third, like 300% of water loss with one leak. Imagine multiple leaks. Fix your leaks, unplug your nozzles, and put regulation. The nozzles could be $1 or $2. It's worth it. And again, when we talk about the nozzle sizes and we don't pay attention when they actually like get worn out, I'm not going to go over math because we're enough for today, but just want to pay attention to this. So the Q is the amount of water coming out of that nozzle, or the flow rate. In this equation, like the D is the diameter of that nozzle, so the orifice, like that water is coming out. If you just see this is squared. So that means that it's really important, because like the amount of water that is coming here depends on the orifice there, the nozzle type. See, if you, for example, have a nozzle type that you need it to be 532s, and they're worn out and they start like increasing size, you can be applying way more water. Instead of like applying here like the 6, you can be applying about 40 to 50% extra water in one single nozzle. So that's really, really important. Check your nozzles, make sure that they are like in good shape. And one good thing to do that, just to check, is do a simple calculation. Just put a bucket of water and turn it on and see in a minute how much water you're actually collecting. That way you can see if you see different patterns or too much water applied in one, you can check if those nozzles are actually applying way more water than intended to be. Deficit irrigation is another way to reduce the amount of water that you should be applying. Most of the crops, so this is pretty much optimizing your irrigation. Like there's sensitive crop stages. In general, like the plants, when they're in reproductive stages of the, are much more sensitive. So, but during vegetative stages, you can actually stress the plant. For example, corn. You can stress the plant during vegetative stages of the crop, and the plant itself is going to look for that water. So it's going to develop more roots into deeper zones to actually uptake more water. So you can stress the plant early in the season, create that big infrastructure, like architecture of your plant, and then later on, when you have the reproductive stages, then you apply the water when you want to protect your yield. So in general, this is a curve that when water is more required during like different crops. So you don't want to apply water when really it's not needed. To understand that, this is a graph or a crop yield response. So over here is yield on the y-axis, and then on the x-axis here is the applied water. So this graph shows that pretty much a 1-1 or a very huge response in yield when you apply more water, right? So over here, any additional water, it's going to create more yield. However, what happens here when we have reached this point, it's almost, I mean, the amount of, so this means like the more water I apply, right, is apply water, the more water that I apply, this is the only amount of yield increase that I'm going to get. So defining this point, defining when your plant actually is uptaking the most of the water but is not going to increase more, is going to help you determine what is your point of, okay, this is the moment that I don't need to apply more water, because any extra water is not going to give me any more yield than in comparison to the maximum. So not necessarily this point is corresponding to the maximum yield, but you can compensate that on fuel, on the amount of energy that you have to put this water. So you can save a lot of water, energy, and labor if you understand this point. And this will vary depending on your crop too. So how to improve it? We really have to measure it. Sometimes we're like, okay, how do you know that you have to put gas in your tank? Only if you actually check, because if not, you're going to be pushing that car, right? So how do we know if the kids are actually growing, improving? And yeah, you have to really measure. The same thing is with irrigation. We need to understand our plants to know where we are in the tank, when we have to actually apply more water or less water. We have to measure it, we have to calculate it. And over here, I'm going to skip this part because we have seen enough math, and I'm going to let Abigail go over irrigation scheduling using soil moisture sensors and tensiometers.
So, John, if you want to come up. Both Maria and I have statewide appointments. John is stationed in this area, so I thought he'd be a good person to... Oh, John, do you want to introduce yourself?
Yeah, so I'm actually not an irrigation specialist. I'm a weed scientist by training, but I'm located at the experiment station, so COARC, Central Oregon Ag Experiment Research and Extension Center, so north of the airport in Madras, and I'm happy to help to the extent that I can. So I serve the local area in addition to Scott and Tracy and other extension people. So if you have local questions, call us at the center. We can certainly coordinate with our statewide specialist. That's part of our role, or help you with local adjustments. Again, I'm more of a weeds person, so I'll do the best I can with irrigation, but we'll try to answer your questions or connect you to the person that you need to talk to. So feel free to contact me about anything, and then we'll direct it from there.
Great. Thanks. Yeah. So this is now technology is working. So as I mentioned, there's two main types. There's something called the soil water tension sensors. And so we have a couple up here, tensiometers. And like mentioned, this is great because it's not just how much water is in the soil, but how much is available for that plant to use. So the way they work is you have a tube, and then at the end, so then there's either a gauge, don't mind my drawing, or you can connect it to a data logger. And then at the end, there's a porous tip, so a porous ceramic tip. And so say this is your soil here. And then if this is dry, you have this ceramic tip at the bottom. And this is filled with water in here. So let's say this is at a water level of here, and this is all filled. Then the water will then move from the inside of the tube outside into the soil, right? That makes sense. If it's dry or outside, the water is going to move out until that equalizes. Since this is airtight, there's a little bubble of air up here. As the water moves out, this moves down. This will now be all air. And that vacuum increases. So the gauge up here measures that pressure in there. And then from that, it correlates to basically how much water is available for that plant. So as the water moves out, it's indicating that there's less water available for that plant. Does that make sense? And the great thing about these is it's one of the few ways that directly measures how much water is in the soil. These, the volumetric water content sensors, it's the volume of water per the volume of soil. And the way it does this is it uses a constant to basically look at the electrical conduction. Yeah, and uses a constant. But this can be affected by things like salinity, by texture. And usually people just install them and just use the default. But you really need to look at what your soil type is and calibrate it for that specific type. Okay, so yeah, this picture just shows again that as it dries, the water moves into the soil, this vacuum increases, and the gauge changes. You could.
People use that. Do they typically put it in just to use it and take it out, or they leave it in the soil?
So the tensiometers, the ones we have, you usually leave them in for the whole irrigation season. You take them out in the winter because these ones can't freeze. But there's also ones up here that are meant to be left in the soil for a long period of time. So it kind of depends on what you're growing, what you want to do. Again, there's not just saying, I recommend this soil moisture sensor for you. It's really looking at your system and what you're trying to do. All right. Go for it. No.
The volumetric sensors, so some are installed. You have to install them pretty carefully into your soil profile. You dig a hole and kind of push, like this decagon sensor here. You know, at the level of the soil you want to measure, you push it in, and that stays installed either through the whole irrigation season or potentially for years. There are others, like this one, that is more of a portable unit. So this would be, you just put it into the top of your soil, and it reads it gives you an estimate of the volumetric content. So there's a range of different commercially available systems, I guess is the short answer. Some are permanently installed, some you can move from field to field.
And the ones here, just a heads up, the voles really like to eat the wires.
That's good to notice. Yeah, also the tensiometers even up here have various setups, so you can read it by a gauge, so just directly looking at the gauge. So that there's a gauge looking.
Manual, some go to various levels of remote systems, so there are a lot of nice commercial systems that you can get on your phone. You know, it's a very nicely integrated app that costs more obviously than something like this where you have to walk and just write down your readings. And there's a full range of options, I guess. So.
Yeah, Irrometer also offers, like, it can trigger, so if the gauge gets too low, you can trigger your irrigation system to come on, but obviously that costs quite a bit of money. But one thing also to point out with looking at soil moisture sensors is oh, was there a question back there? Sorry.
I was just curious about the basic cost of like one of these tensiometers. What does one cost?
I think the tensiometers cost around $100 a piece. Is that about right?
Yeah, probably up from there. So there's a range of costs. The volumetric sensors tend to be more. I mean, you're looking at maybe $300 to $500 for a system that works. You can go on Amazon and there's cheap stuff, but those really are not worth wasting your time or money on. They're so inaccurate that you're gonna.
At that point, it's almost better just to dig the pit and see what the water is.
Whatever happened to the shovel in the hand?
You can do that, yeah. But
if you're just based on it, so there's a whole continuum from, you know, free, just shovel in a hand or calendar date, all the way up to very sophisticated, accurate, and expensive systems that take a lot of expertise and time to set up. And so, you know, start where you're at and see if you can make the improvement with the money you can invest and the time you can invest. And, you know, as you get more and more sophisticated, there's less and less returns from more investment, but you can save that last few percent or whatever you need. So think about your systems and what would make sense for you. And so this is a general overview. You know, if you have specific questions for your operation, talk to us individually and we can try to help you, you know, give some more tailored recommendations like this.
Yeah, because the benefit is as water gets tighter and tighter, these really help you narrow in on how much the plants actually need. And as Garrett showed with that irrigation scheduler, there's spots where you can go in and input your volumetric water content on those days, and then it will update based on that how much water you need. And so you can go out with a shovel in your hand and look how much it is, but unless you want to go out every day, every season, it's not also going to give you exactly how much is there and also how much the plant can use. So one thing also to note when looking at the sensors is You can't just put it at one location for all crops, all fields. So as Maria pointed out, you have different rooting depths for the different crops. And so if you put one, say, at a foot, maybe it won't tell you as much based on, say, lettuce versus grass seed or something like that. And so, for instance, this shows 3 different tensiometers and the water at the different levels. So say you just have one installed here, and that's all you're reading from. Well, it's going to look like the plant isn't getting any water, when actually it probably is. So also this goes back to what we've talked about quite a bit. So this correlates the available water depletion versus what is measured on that gauge over there. And so as Garrett pointed out, with the lettuce, you want around a 25% allowable depletion. But for most crops, okay, I think that's working now. Okay, well, this one just shows for the different crops what you want to keep in this optimal range. So for instance, something like strawberries, you really want to keep it with that low pressure just because it needs a lot of water, as if you compare it to grains, which need a little bit less water. And then as we talked about for that available water depletion, you want to keep it around 10 to 50%. That's the general range for a lot of crops. Okay, now it's going backwards. Okay, yeah, so for instance, if you, in this range, so you want to keep it, say, 50% allowable depletion, and you have a sandy soil, that's going to read 25 kilopascals on your gauge. As opposed to something, if you have a clay with that 50% depletion, it's going to be reading 250 kilopascals. Because again, when you have that tighter soil, it takes a lot more pressure to extract the same amount of water, as opposed to something like a sandy soil. Does that make sense? So then this is an example looking at how you can do irrigation scheduling based on your volumetric water content. So again, that's looking at the percent of water to the amount of water per the volume of soil. And so from looking at this goes back to what we've talked about before. You really want to keep that soil moisture sensor between the field capacity and the maximum allowable depletion. So these are these 2 lines here. And as your volumetric water content starts to get down below to hitting that maximum allowable depletion, you want to then schedule your irrigation event. So again, this is when it's really helpful to use those sensors to see how much water is in your soil to know when exactly you should turn on your system. Right, so that between those is the readily available water for the plant. And so for instance here, you can look at your volumetric water content, and those 2 periods, the red lines, represent when irrigation events happened. So you can see then you irrigated, you can bump it up to that field capacity, and that's a good situation. But then if you look at here, your water starts to deplete, but then you have a rainfall. So then it pops that volumetric water content up. So then you obviously don't want to irrigate because there's plenty of water for the plants. So don't irrigate then. And then again, you continue your irrigation when you extract more of that water and the plant needs more water, so then you irrigate. Does that make sense? And this example is for a sandy soil, so one that's really responsive to watering into these events. Does anyone have any questions? Yes?
I'm just curious if there's already some charts or something that exist. Like I do lots of different vegetables, and I'm thinking in my head, I need to create a chart of the allowable whatever depletion for different crops and create categories and things to help myself. Does that already exist?
Yeah, it does. And also with that irrigation scheduler, it should be helpful to look at the different crops and to look at when you need to irrigate with that. But there are those available. Maria, do you know the sources you can look for that information off the top of your head? So she's asking for different crops, like what that curve would look like with when you need to irrigate based on volumetric water content. And
yeah, there's some published information. FAO has some that are very generalized and should be more into localized. Agrimet stations also have what I use that you can also determine how much is that particular crop in that particular location will be extracting water to. If you go to the Agrimet station, there's a section over there that has crop water use, and you can actually get some information. But yeah, right at the top of my head, those are the 2 main sources that you can get.
This insight is good for us to know too if there isn't a readily available source. Maybe it's something to work on to compile this and make it accessible for people. So if you guys do notice things like this, that some shortcomings in available information, let us know and we can hopefully find that information for you. So yeah, Maria, ask her about your irrigation questions. I am not an irrigation specialist. My title is the Soil and Water Quality Specialist, which is why I'm going to present to you now about water quality. But yeah, feel free to reach out to us. Feel free to reach out to your local extension agents. We're here to help you guys and need to know like what's important to know in the field. Okay, so I am speaking again, so I'll now be talking about water quality. So this presentation is based on, there's an extension document that talks about irrigation water quality for your management. And I think one thing that people forget when you think about water quality, it's kind of a politicized word right now. And you forget that it's also important when dealing with your crops and your practices. And so this goes through and looks at how you can analyze your water quality and how that will affect your irrigation and your soil structure and your overall crop health. And so we're currently working on updating this, this extension document, but it is available online if you have further questions about this. So first of all, I would like to ask you guys the question, do you have any concerns about your water quality? Yeah. No concerns. Okay. Who has any? Really good water. Yeah? Okay. Well, that's good to hear. Okay. What's your source? The Deschutes. Okay. I think. Yeah.
I guess a concern I have, if we have a drip system and that's being fed from a pond,
yeah.
I guess my concern would be like algae growth in my drip system.
Perfect. Okay. Yeah. So this question comes about. So, oh, yeah. Yes.
I'm concerned about everybody around me using pesticides and herbicides in the water.
Yeah, I've heard that one too. But this is good to think about. And so this question came about, Maria and I are both new to Oregon, so we spent the past year traveling around talking to people about their irrigation and their water quality. And a lot of growers came to me and said, yes, we have problems with fouling of our nozzles, we have problems with clogging of our system. And then when I asked, do you have trouble with your water quality, almost everyone said no. And to me, there is a disconnect between that of like, you hear water quality and people tend to think it's, like I said, a little bit politicized, but it does affect the people around you and it also affects how you irrigate. We should all be concerned about water quality. And so from that, this picture comes about. So if looking at this, if you have problems, for instance, with dirt and algae clogging your filters, if you have problems with this picture on the bottom is like lime deposition, which can then clog your nozzles that way. Corrosion of your system depending on your water pH. And these might indicate a problem with the quality of your irrigation water. So when you're looking at this, some important parameters to pay attention to is your nutrients. This is also great to consider because if, say, I know a lot of people around here use groundwater, not maybe in this area, but in Oregon as a whole, some of that groundwater can have high nitrates. You could almost use that for your advantage and apply less fertilizer. And these days when fertilizer costs are kind of through the roof, any nitrate that you can get without applying more is a good condition. Your pH, so both low and high can have implications for your soil and crop quality. The potential salinity issues, sodium hazards, which is different from your salinity. Your salinity is just basically how many salts you have in your water, whereas that sodium is purely how many sodium ions you have in your water. Suspended solids, so as mentioned, if you have things like algae in your water, that can then cause clogging of your system. And so poor water quality can have potential risks to both human and environmental health, as mentioned, and can also have impacts on your crop health. And so from looking at this picture, oops, this top two represent figures of potential salinization. So if you look at your soil, you can see that white residue on the surface. And also this picture was taken, I think around here, and a lot of people pull from these irrigation ditches, these unlined ditches where you can have a lot of sediment and clog your system that way. So you really, especially if you're using micro irrigation, if you're using drip irrigation, you really should have a filtration system in place. All right, so the potential impacts of poor water quality. So again, you can plug those filters. You can plug your filters and your emitters. You can slow your infiltration and destroy your soil structure. So that's largely if you have problems with your sodium hazards. You can destroy your soil structure, which then affects how much water infiltrates. You can get hard pans where then the water infiltrates slower. You can affect your nearby groundwater and surface water quality if you're applying things at the wrong time. if you're irrigating at the wrong time. I had a demonstration to look at how applying the different fertilizers will then, based on your soil type, how fast that will leach through. For instance, if you apply a fertilizer on a sandy soil and then you irrigate at a high rate, that's all going to wash through your soil, as opposed to something that's a clay soil or a silty soil that will hold the fertilizers better. All right. And so also looking at your irrigation water sources, does anyone around here use groundwater, or is it all surface water? You use groundwater? Okay. Yeah, so usually groundwater has problems with carbonates, and you have to then look at your lime deposition potential. You have to look at the clogging. With surface water, you have to look obviously with things like turbidity and your clogging of your systems. And also, it's a lot more variable over time. So in the spring, with heavy rainfalls, with snowmelt, you can have more turbid systems and more potential for clogging. Right, so this is just another picture of your turbidity measured in different ways. So for lakes and reservoirs, you can use a really simple system called the Secchi disc, which is basically just this little disc that you put down in the water and measure how deep, very technical, how deep you can see it till. You can also go and take samples and look at the basically the reflectance, the clarity of that water. Right, so again, this just correlates. Again, there's a high correlation between your seasonal characteristics, your water flow, and those turbidity, that turbidity level. So for this, the things that you should do occasionally is just analyzing the irrigation water quality, looking at the reports. This is especially important for groundwater and really only needs to be done occasionally. Determine the water limitations based on your crop, soil, and system, and look at, if you have trouble, how you can manage that system. I've been getting reports from groundwater as water restrictions increase. People are looking for alternative sources and trying to weigh whether or not that alternative source can be used. Sometimes the quality of that water is so poor that it really shouldn't be used to irrigate. And this is especially important if you have issues with salinity, with salts, because once those salts are in the soil, there's really not much you can do. The only way really is to flush the soil and get those out, which if you have problems with water restrictions, obviously that's hard to do. All right, so this is just some different parameters that you can test for your water quality issues. Yeah, and with that, that is the summary of the presentation, and especially since it's 12 o'clock, so I tried to go fast. But yeah, if you guys have any questions, so looking at your soil, how you irrigate, how you apply your fertilizers, and understanding that relationship is really important. So yeah, that is my summary. Yeah.
I just want to say thank you so much to our presenters. Can we give them another round of applause? Thank you so much for all of you for being here today. This was funded by the USDA Beginning Farmer Rancher Development Program grant under the National Institute for Food and Agriculture. There's a lot of other upcoming educational opportunities. There's some disaster relief coming up as well. I'll stick around if you guys have interest in that. And then Deschutes Soil and Water and Conservation District is putting I think 3-part series on irrigation coming up, I believe, in April. So please do register for that, and I can help get you in contact with Todd again. And with that said, thank you so much. I hope you have a great day, and we are praying for snow, right? Thanks, guys.